little bit of progress on chapter 4. Okay. So, the beginning of chapter 4 is going to feel like a lot of review, which is good. But we have to kind of sort of go through this stuff with sequences and summations because a lot of the induction proofs that we are going to do are going to be concerning summations because it's a very good proof technique for those. So that's why we're doing all of this review and getting these definitions back in a familiar standing with ourselves. Okay, so probably you've seen this before. A sequence is just a special kind of function. The domain is going to be a consecutive set of integers. The two most popular are using 0, 1, 2, 3, or just using 1, 2, 3, 4, 5, and so on and so forth. Okay, so depending on how you like to define the natural numbers, you might, so computer scientists generally tend to have their domain be the natural numbers starting with 0. Okay, other people who define the natural numbers starting at 1 will have their domain be the natural numbers starting at 1. But in general, the domain will be the natural numbers. And then what we would do for this function is to each element in the domain, we map it to some output in some element. So for here, like if we put in 1, okay, the output would be 1. When we put in when we put in 0, the output is 1. When we put in the next input 1, our output is also 1. When we put the input in 3, we get the 2, we get 2. When we put in 3, we get 3. When we put 4 in, we get 5. Okay, and so our function just goes to each item in the domain and associates some output with it. And then the outputs here, 1, 1, 2, 3, 5, those would be what we call our sequence. Okay, so that's a lot of notation. And so it's kind of hard to look at that and see any patterns or see what's going on. So often we use subscripts instead of the parentheses, like the typical function notation. So here, if we said f, and then put a subscript of 0 and say f sub 0 is equal to 1, okay, that says, okay, when we use the 0 from the domain, okay, the output that's produced for the input of 0 is 1. And this is just like this one. The output that is produced for the input of 1 is 1. The output produced for an input of 2 from the domain is 2, and so on and so forth. Okay, so this just abbreviates the notation a little bit. Okay, with the subscripts, it's just like this. It just is abbreviated because you don't have to have the parentheses. Okay. And so we can easily see, okay, the f sub k is called a term. Okay, whatever the subscript is there is called the index. So I call it like the 0th term, the 1 term, the 2 term, so on and so forth. Okay. And if I put little brackets around f sub k, that means I'm talking about the entire sequence. Okay, if I don't have any brackets around it, I'm just talking about a single term. Okay, so for instance, if I were to do fk like that, okay, that would be these values. 1, and then 1, and then 2, and then 3, and then 5, and on it goes. You may have seen those numbers before. It's a famous sequence. But that would be like the shorthand notation for that particular sequence. Okay. So a couple more. So if we have a finite domain, okay, where we start and then have consecutive integers starting at m and ending at n, but it's a finite sequence, okay, with a finite domain. So if there's a finite domain, then we have a finite sequence. We call the first index in the domain the initial index, and the last one, the largest value in the domain, the final index. Okay. And then the term associated with that index, so those would be the initial terms and the final terms. Okay. And of course, a lot of times we're talking about infinite sequences that start somewhere, but they just keep going on and on and on forever. So if you have an infinite domain, you will have an infinite sequence. Okay, so of course there's like initial term, but there is no final term. So you've probably seen the term sequences before. You might not have seen it written out in function notation, but you've probably seen it in subscript notation. Okay. And you probably have the idea of what finite and infinite sequences are. Okay. Now with sequences, it's nice, if I just write out the sequence like this, so a sub k equals, and then I just use sort of a set builder notation kind of thing where I kind of establish a pattern and put a dot, dot, dot in there. You can see pretty easily probably what the next term would be in that sequence. So, it goes 0, 1, 4, 9, 16. What's the next term going to be? $25, yeah. So these are just perfect squares, right? Okay, so hopefully you get the idea. So this is the first perfect square, starting at 0 at least. The next perfect square, the next perfect. These are just a bunch of perfect squares. Okay, so we put enough values in there that you can establish a pattern and put a dot, dot, dot. Okay. So it's nice if we have what's called an explicit formula, where I can just give you a formula that tells you how to calculate the value of a sub k depending on any k. So notice this is the domain is 1, so this is a sub 1, this is a sub 2, this is a sub 3, a sub 4, a sub 5, and on they go. Okay. But rather than writing out this long, establish a pattern and then you have to figure out what the pattern is, it would be nice if there was a formula there to tell you what the pattern was. Okay. And so imagine we were trying to be nice to somebody and just write a formula, an explicit formula to tell them how to find any value a sub k. Okay. So think about it. When I have the input of 0 from my domain, the output value the input of 1, the output has to be 0. When I have the input of 2, the output has to be 1. When I have an input of 3, the output has to be 4, and so on and so forth. So what's the relationship? What do I have to do with the index there to get the output?
Index times index. Index times itself.
Okay, really close to that. Yeah, so index squared. But if I do 1 squared, I get 1. If I do 2 squared, I get 4. If I do 3 squared, I get 9. I'm always getting the next one instead of this one.
Index minus 1 squared.
Yes, good, perfect. So we have to take the index, subtract 1 from it, and then square that quantity. Okay, so if I try that one out now, so if I put a 1, so a sub 1, so where k is 1, I do 1 minus 1 is 0, 0 squared is 0. Yep, I get 0. Okay, what is a sub 4? So a sub 4, okay, I put 4 minus 1 is 3, 3 squared is 9. Sure enough, it's 9. Okay. So, I've only checked 2 of them, but hopefully you can see that that's going to work. Okay. And so if I have a formula like this, I can say, here's the sequence a sub k, where a sub k is defined like that. Okay. So that will tell me exactly how to find all of the values, and of course you'd have to know what the domain is, so well. Okay. All right, so let's say I tell you we've got a sequence, okay, and I want to find the 5th term of the sequence, and it's defined by a sub k equals 2k minus 1, and the domain is 0, 1, 2, 3, and so on and so forth. Okay. What makes this question tricky is starting at 0, okay, because you probably feel like, oh, I want to find the 5th term, so I should just put 5 in for k, and that will tell me the 5th term. But if we're starting at 0, what will the index of the 5th term be? Exactly, 4. Okay, so the index of the 5th term is 4. So we just have to be really careful and look at what our domain is. Okay, we're used to this from all sorts of loops that we write and everything. If I want to go through a loop, 10 times, I make it go 0 to 9, right? So you guys are computer scientists. This isn't going to throw you off. Okay, so if I want to find the fifth term, that's actually a sub 4 when the domain starts at 0. Okay, so that would be 2 times 4 minus 1, oops, okay, which is 7. So it's just important that we look at the domain and pay attention to whether it's starting at 1 or starting at 0, so we don't get thrown off by trying just to think that the fifth term will always be k being 5. Okay, we have, these are pretty intuitive definitions, so this shouldn't throw us off. So a sequence is, yes?
Can you go to that real quick? So it wouldn't be a of 5?
No. Okay, because, so if, here's my domain. It goes 0, 1, 2, 3, 4. This is the first term. This is the second term, third, fourth, this is the fifth. Yeah.
Okay, I just got the notation.
Yeah. We love to start at 0. Okay, so an increasing sequence is if you look at the sequence, okay, and then anytime you have two consecutive indices, k and k plus 1, okay, the kth term is always strictly less than the k plus first term. So, for example, if we go back to like this one, the 0, 1, 4, 9, 16, okay, so whenever I look at any two consecutive terms, like here and here, 0 is less than 1, 1 is less than 4, 4 is less than 9, 9 is less than 16, 16 is less than 25, and you can imagine as it's going on, any two consecutive terms that I pick, okay, the first one is always going to be less than the one that's after it. So this is an example of an increasing sequence. Okay. But this other one, where I had 1, 1, 2, 3, 5, 8, and on it goes. Anybody know that sequence, what the name of it is? Yeah, those are the Fibonacci numbers, right? That's the Fibonacci sequence, okay? This one, on the other hand, okay, notice, so if I look at this, like, you know, 5 is less than 8, 3 is less than 5, 2 is less than 3, 1 is less than 2, but when we get to here, 1 is not less than 1. Okay, so this right here gives us trouble. We don't have consecutive terms in which the first term is less than, strictly less than the second one. So this is not an increasing sequence. Okay. So we also have a sequence that is called non-decreasing. Okay, and notice the only difference between these two is the use of the equal here. Okay. So it's not necessarily an increasing sequence, okay, but the values are never getting smaller. So for a non-decreasing sequence, if we go back to our Fibonacci numbers, the 1, 1, 2, 3, 5, 8, and on it goes. Okay. This time the definition works, okay. We've got two consecutive terms, and the first one is less than or equal to the second one. Okay. And then here, it's strictly less than. The rest of them are all less than. This is the only one that is equal to, but it still fits this definition. So this is not increasing, but this is a non-decreasing sequence. And then, as you can imagine, decreasing and non-increasing are defined in a similar way. A decreasing sequence, okay, if you look at two terms, the first one always has to be strictly greater than the second one. And as long as it's greater than or equal to, then it would be called non-increasing. Okay. So it never gets any bigger. It's not getting strictly smaller, but as you're moving on, it never gets bigger. So that would be like the non-increasing. And the last thing we need to look at in terms of sequences are two special kinds of sequences called arithmetic and geometric sequences. Okay, so an arithmetic sequence is a special kind of sequence of real numbers in which when you look at two consecutive terms and you look at the difference between them, it's always the same. It's constant. So for instance, if I look at the difference between 5 and 2, it's 3. The difference between 8 and 5, 3. These two, the difference is 3. These two, the difference of 3. Okay, so the difference between any two consecutive terms is always 3. There. So that 3 would be called the common difference. That's what our common difference. So this is the common difference. Okay. And one of the nice things about an arithmetic sequence that's like this is that you can find an explicit formula. So, you know, if I have a sequence like this and I ask you, well, what's the 107th term in this sequence? Well, you don't want to have to add plus 3, plus 3, plus 3, plus... You don't want to do that for, you know, forever. So it'd be nice if you just had a formula that could tell you, if I want the 107th term, I just plug it into this formula and it tells me what it is. Okay. I think that the formula is fairly intuitive. So if you want to get to the kth term, how did you find the kth term? Okay, well, you went to the first term. That's where it all starts. And then you had to add on the common difference, which we call D. This D is the common difference. Okay, and you have to add on the common difference, k minus 1 times, to get to the kth term. Okay, so this is just telling you how many 3's you would have to add on to get up to the kth term. Okay, so a fairly intuitive formula. Okay, this is for if the domain is 1, 2, 3. You have to slightly tweak this definition if you start at 0. Okay, so if you start at 0, you have to change this to be k instead of k minus 1. Okay, but other than that, you know, this is probably, if you've ever seen this formula, that's probably the way you've seen it written. Okay, and then we also have a geometric sequence. Okay, so a geometric sequence is a sequence when the ratio between two consecutive terms is always constant. So here's an example. We've got this sequence 3, 6, 12, 24, 48. And so if you look at the ratio of 6 to 3 is 2. The ratio of 12 to 6, 2. The ratio of 24 to 12, 2. Okay, you can see every time the ratio is exactly the same. So the ratio between any two consecutive terms here is always 2, and that's called the common ratio. Now it has to be consecutive terms. They have to be right one after another. And so the formula that we could use to find a specific term in a sequence is very similar. Okay, so notice here we just started with the first one and we had to add on a certain number of common differences to get to the kth term. Here, because we're multiplying every time, you know, we have to multiply by 2, multiply by 2, multiply by 2. So we start with the first term and we have to multiply by the common ratio a certain number of times. Well, k minus 1 times to get up to these. If you start at the first one, you have to multiply by the common ratio, k minus 1 times to get up to term k. Okay. So they're both, you know, here, the only difference, this one you're adding a common difference, k minus 1 times. Here you're multiplying by a common ratio, k minus 1 times. So those are special kinds of sequences, but not every sequence falls into those two categories. These are very special. So like the Fibonacci one that we've seen, okay. Okay, there's a couple different definitions, but you know, Fibonacci's original one started with 1, 1, 2, 3, 5, 8, and on it goes. The other way you'll see it is 0, 1, 1, 2, 3, 5, 8. So either one of those would be, okay. called Fibonacci sequence because they have the same numbers. It's just that this one starts at 0 instead. Okay. But notice, if I look, is this an arithmetic or a geometric sequence? Well, am I adding the same number? Well, no, the difference here is 0, the difference is 1, the difference is 1 again, the difference is 2, the difference is 3, right? So we don't have a common difference where it's always the same, and certainly the ratios aren't the same. Yes? Probably the top one is more common, okay? Like the Fibonacci numbers show up all over nature and stuff like that, and so usually, like, you know, Fibonacci originally did this when he had, like, looking at the reproduction of rabbits, and if you started with 0 rabbits, you wouldn't reproduce at all. So, like, it doesn't make sense there. So usually it starts like this. But there's other contexts where you might want to start it at 0. It's just the top one is more of the original, and like when you see it in nature, that's the one that you're seeing. But okay. Pine cones, pineapples, flower. If you ever get into numbers, it's everywhere. Okay. Okay, so that's our whirlwind review of sequences. Hopefully most of that stuff is stuff you've seen before. You're like, oh yeah, I remember seeing that sometime in my past. Okay. All right. And so, recurrence relations, you might have seen some of this as well, maybe not. Okay. So, we like explicit formulas. They make it really nice for us to be able to, like with the arithmetic sequences and the geometric sequences, it makes it really easy to find a specific term in that sequence. And so it would be nice if you could have explicit formulas, but the Fibonacci sequence, if you actually found out the formula for finding the nth term in a Fibonacci sequence, it's this crazy thing right here. It's so fun. I just thought I'd share it. Like, would I ever expect you to find a formula like this? No. Like, you have to kind of do some advanced mathematics to be able to come up with this formula. But there's this phi to the nth power divided by the square root of 5 plus 1/2. And then you take the floor of that, and magically, somehow, it gives you the nth Fibonacci number. Okay, and phi is this, mathematical term called the golden ratio. Maybe you've seen that before, where it's 1 plus the square root of 5 over 2. Okay. This is also one of those things that just shows up all over nature everywhere, so it's called the golden ratio, because it's everywhere. Okay. But, like, we're never going to come up with an explicit formula like this, because this is, way too advanced for us. We're not there yet. Okay. And so, it's not always natural or very easy to find an explicit formula, but we can often find what's called a recursive formula or a recurrence relation to describe these kinds of sequences. Okay. And a recurrence relation just defines a term of the sequence based on previous terms in the sequence. Okay, so for example, our Fibonacci sequence, if you had to just describe to me, like, how am I going to find the next term in the Fibonacci sequence? Yeah, what is it? Yeah, you just take the last two. So if I want to get the next one, I take 5 plus 8, and the next one is 13. So notice how I do 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. So we're always taking the previous two, adding them together to get the next one. Okay, and so I can so that's kind of the idea of a recurrence relation. So a recurrence relation gives me a way of looking at previous terms in the sequence and telling me some kinds of operations to do to them to find the next one. Okay, so it's not an explicit formula because it doesn't just rely on its position in if it's the 17th term, then it only relies on the number 17. Like, that's an explicit formula. A recurrence relation says if I want to find the 17th term, well, I can tell you something about how to get that from maybe the 16th term and the 5th, some previous terms. Okay. And you probably have, if you guys are programmers, so you go, oh, this has recursion written all over it, right? So this is all related to recursion. So let's try a few different recurrence relation examples. So let's say I have an arithmetic sequence. If you think about the way that works, let's go back to our example. Okay. So if we had to describe a rule of how I was going to find, like I want to find the next term after that, well, the rule would be like what? What do you do? Yep. Yeah, so you go to the previous term and you add 3 to it, right? Okay, so in general, you would say, okay, well, if I want to find the nth term in an arithmetic sequence, I'm just going to go to the previous term. Well, the previous term is the term that has index n minus 1, and then I just add the common difference onto it. Okay, so that's what that would look like. Now, you guys know about recursion, and you know, like, you know, if you were to try to write that into a program, you would get infinite recursion. You have to have a starting point where, you know, your recursion will go on forever. Same thing with recurrence relations. So I have to say, like, where to start. Okay, so I might say, like, a sub 0 or 1, wherever I want to start. We're computer scientists, will start at 0. If I tell you, okay, well, the starting point is, and then I pick some constant, you know. So here is, this is called my initial value, or my initial conditions. Okay, and then this is my recursive rule. Okay. So for instance, if we go back to this one right here, okay, if I wanted to find this sequence, well, I'd say, okay, well, everything starts at 2. That's kind of my anchor point. So I would say, all right, well, the first one, a sub 0, is 2. Okay. And then if I want to get to any other number, I'm just going to take the one before it, and I'm going to add, well, if I want to get to the next one, I have to add 3 in this particular instance. So I'd have to add 3 to it. Okay, so this is like an example of ours. So notice, if I want to find a sub 1, I'll go, well, a sub 1 is a sub 0, which is 2, plus 3, which is 5. Okay, sure enough, that's the next number in the sequence. Okay. Now, of course, the trouble with this, okay, is if I want to know the 7th one, I have to know the 6th one. And if I want to figure out what the 6th one is, I have to know the 5th one. But if I want to know what the 5th one is, I have to know the 4th one. And it goes back and back. So it's much harder to generate individual terms using a recurrence relation than it is an explicit formula. With an explicit formula, you just plug in the number, you have one little equation, and you're done. When you have a recurrence relation, you have to trace this whole path back until you get to numbers that you know. Okay. So we could also do a recurrence relation for a geometric sequence. Very similar. So think about this geometric sequence. Once again, we would just say, okay, I have to have a starting point, like here with the 3, and then you could write a recursive rule. Well, if I want to find the next value in the sequence, I just take the previous one and multiply it by 2. Okay, so I would say, okay, I have to have some kind of initial condition, and then to find the nth term, I just go to the previous term, which is a sub n minus 1, and then I multiply it by the common ratio. Okay, so once again, I have some kind of initial value, and I have a recursive rule. Okay, so for our example here, okay, where we had the 3, 6, 12, our initial condition would be 3, and then our recursive rule would be I take the previous one and multiply it by 2. And then let's think about the Fibonacci sequence, like these ones right here. Okay, so we already talked about the recursive rules. If I want to find the nth term in the Fibonacci sequence, so if I want to find this one, I've got to go to the one before it and the one before that. Okay, so if I'm here and this is n, this is the n minus first term, this is the n minus second term, right? So I have to take the n minus first term and the n minus second term and add those two things together to get the nth term. Okay. Now the thing that's tricky about this, okay, is normally here I could just have an initial condition, but down here, let's say I say, all right, f sub 0 is equal to, let's do this one. Let's do this one where f sub 0 is 0. Usually this one maps to 1, 2, 3, and this one maps to 0, 1, 2, 3. Okay. So let's say I only had just that initial condition. And now I said, okay, well, now I want to know what f sub 1 is. Well, to find f sub 1, I add f sub 0. I know that's 0. And f sub, well, if I put a 1 in there, I'm going to negative 1. I don't have an f sub negative 1. Okay. So because I have to go back 2 spots from the current position that I am, I need to have 2 initial conditions. 1 is not going to do it. I would have to list 2 initial conditions, an F0 and an F1, okay, being 1. So I'd have to have both of these as my initial conditions, and I need 2 things to get the sequence started. Okay. And now, the first place that I can apply my recursive rule would be the next spot at F sub 2. So if I want to find f sub 2, that would be f sub 1, which is 1, plus f sub 0, which is 0. Now I can do the rule. Okay. So look, depending on if you just look at the smallest index here and see how far away it is from the index you're trying to compute, that's how many initial conditions you're going to need. Okay, to kind of like get the pipeline flowing and get everything started. So for those initial values, the number of initial values that you need, okay, depends on how many previous terms you're using in the recursive rule. So there's another famous sequence called the Lucas sequence. Okay, it's very similar to the Fibonacci sequence. Okay, so notice the rule is just the same as Fibonacci, really. It takes the previous 2 terms. L sub n minus 1 is right before n, L sub n minus 2 is the one before that, and adds them together. Okay, so if you look at this, okay, this is the smallest index, and it's a distance of 2 away from the index I'm trying to compute. So how many initial conditions am I going to need? 2, exactly. We need 2 of them, just like we did with Fibonacci. Okay, and so L sub 0 for the Lucas sequence is going to be 2, and L sub 1 equals 1. That's how it starts off. So if you were to look at the Lucas sequence, it starts out 2, 1, and then you always add the previous 2 numbers, right? So to get the next one, okay, I would take 2 plus 1 is 3. To get the next one, 1 plus 3 is 4. I would get 7, 11, and 18, and so on and so forth, and on it goes. Okay, this also shows up quite a lot, kind of a famous sequence. One thing interesting about this one is it an increasing sequence? No. Is it a non-increasing sequence? No. Is it a decreasing sequence? No. Is it a non-decreasing or non-increasing? It's actually none of those. Okay, so it's tricky. So notice it goes down here, so it decreases, and then it starts increasing. Okay, so it doesn't consistently do one or the other. Okay, so it's none of those 4 things that we discussed previously. It's actually none of those. Okay, so Fibonacci is non-decreasing, but this one, sometimes it decreases and it increases. It doesn't do anything consistent, so it's none of those things. Okay. The Padavin sequence has this recursive rule. So to find the nth term, you go to the term that's 3 positions before it, plus the one that's 2 positions before it, and you add those 2 together. So how many initial conditions are we going to need on that one? Yeah, I heard somebody say it. We need 3, right? So if you look, this is the smallest index. It's 3 away from this one, so you're going to actually need 3 initial conditions on that one. All right. Yes?
I got a question about the Lucas. How's that different than the Fibonacci one?
Because the initial conditions are different. That's all. So the initial conditions of the Fibonacci would be either 1, 1 or 0, 1, depending on which way you like to define it. Okay. But Lucas has just different initial conditions. The recursive rule is exactly the same, but you get a completely different sequence because the initial conditions are different. Yep. That's why the initial conditions are so important, because sometimes you can have the same rule, but if the initial conditions that start things out are different, you'll get a completely different sequence. Yes?
How does the Lucas sequence show up in Matrix?
I'll have to look it up for you, but it's one of those things, like it shows up, I think, on flower petals. Is one of the places that I recall. I can't remember where else it shows up. I think if you Google it, you'll see it. I can't remember I think flower petals. It might be also the tree branch, like when you get branches and they come out and they divide and then they divide and stuff. I think that it's there too. Yeah, there's different, like, I'm pretty sure, like, the pineapples and pie cones are Fibonacci, and I think the flowers and the trees, I think, are Lucas. But I'd have to look it up to remember. Okay. All right. So there's lots of systems in which we see, like, these kinds of sequences where the current state of the system is going to depend on a previous state of the system, okay? And that's called a dynamical system. So any point in time, okay, where the state of your system is defined by rules that depend on a past state of the system. Okay. And then it's called a discrete time dynamical system if you divide your time into discrete intervals. So one of the places that we see this show up a lot is in, like, calculating interest rates. So this is a good example for us to look at. Okay, so if you go and you're trying to figure out the balance of your money that's in the bank, okay, and you're looking at, okay, well, what will the balance be on an account that earns 2% annual interest if the interest is compounded quarterly? Okay, well, there's actually, this is a discrete time dynamical system because they're only paying you your interest every quarter of a year. Okay, so 3 months go by, they give you interest. Another 3 months go by, they give you interest. So this only happens every quarter. So if you get your bank statement and you see you only get it, interest every quarter. So the way that they do that, okay, they'll say the amount, okay, after Q quarters. So I'm just going to use my index to be the number of quarters. Hopefully it helps it be more intuitive. So what are they going to do to figure out how much you have now? Well, they're going to take the amount that you had in the previous quarter. Okay. And then they're going to apply interest to that. So they're going to increase that. So they'll give you, you get 100% of that back plus interest on it. Okay, now this is a 2% annual interest, and since they're doing it quarterly, they're going to take that 2% and divide it by 4. Okay, and that's how much interest, so that's, the effective interest rate for that quarter. But they do it 4 times a year, so, actually, if they only did it once a year, you'd be worse off than if you do it quarterly, okay, because you are actually getting interest. So that is, their recursive rule, but of course, because we have this recursive rule, we need some kind of initial condition. Okay, so A sub 0, when 0 quarters have passed, that's like the principal or the amount that you've put in. So this would be the principal that you're earning interest on. So that's the way that interest is calculated. This, in general, is the amount after Q quarters would be the amount from the previous quarter times 1 plus the interest rate over 4. Okay. It was just 0.2 here because of the 2%. Okay, the other time where we earning money, okay, but of course, usually most of us are losing money, not earning money. So maybe you have a student loan, a car loan, a house payment, whatever, something that you have a loan on. So let's look at how you might look at a recurrence relation for that. Okay, so this one, let's say we have interest that's compounded monthly. Okay, because they're charging you interest, so they'd like to charge you interest more often, so they're going to do it monthly instead of quarterly. So if you think about, all right, so the outstanding balance, or the amount that you still owe after M months. Okay, so here I'll have my index be by months. Yeah. So this one I'll have my index be the number of months. Okay, so what would they do? They would go, okay, well, what was the balance that you owed in the previous month? And they're going to charge you interest on that. Okay, so they're going to, basically do what they did up here. So they're going to charge you interest. So if it's 5%, and since they're doing it monthly, they'll divide that by 12, because they'll do that 12 times every month, or 12 times every year, because this is an annual interest rate. Okay. And so essentially that's the new amount that you owe, but then you make a payment, and so they would subtract off whatever your payment is. Okay. So that would be a recurrence relation that you could write for the outstanding amount on the loan. Once again, this is based on a previous term, so I need an initial condition. So my initial condition would be the initial amount of my loan. I'll just call it L. That's the amount of the loan. All right, so we will, we see these kinds of things come up in our everyday lives all of the time. Okay. That's all we have time for today. Next time we'll do a review of summations, and then we'll get onto some induction proofs, which are super fun. I hope you will enjoy those. Sections 4.1 and 4.2 will be due before class tomorrow. And probably we will have a quiz over proof techniques from Chapter 3 next Tuesday, so just be thinking about that. So, like proof by contrapositive, proof by contradiction, those things. So don't forget about those. Don't repress those.